Hi, welcome back to the channel. Today we're going to be talking about waveform properties, specifically waveform names, so the actual name of every channel in your DAQ task. But before we get started, please show some support, drop a like, throw a comment in the comment section if you have any questions or any ideas for future videos, and of course subscribe to the channel to make sure you're up to date with the latest content. So with that being said, we're going to go ahead and start. I've already prepared the code for you this time. And as you can see, we'll start with this VI. So this is a VI that I created and it takes an input of a waveform. It returns that same waveform as duplicate out, and it gives you the waveform name out. And we'll explore that in a second. We go back to our little simple example. We already have a max task set up, which is this one. With a couple of channels. In this case, one of them is a global virtual channel. And we're going to basically read from that n channels, 1D waveform array, n samples, and we just want to get the name. And we're going to do everything similar to previous videos, except for now we're extracting the name. And if we open this up, so this is going to be a clone. I've set this up as a pre-allocated clone, just so it can be used in multiple places at the same time. And the code is fairly simple. It's a get waveform attribute, and this is a key that exposes the channel name. So we feed in the name, which is the ni underscore channel name, and also we overload the type, so the default value, which is going to be a string, and out is going to be our waveform name out. Now, if we really cared, we'd put an empty string here to overload as a default value. In this case, I didn't do that because we're only working with DAQ tasks, so I just kept it as this, because if this were not to be found, you'd return ni channel name. Not the end of the world, but in this case, for a simple example, I just wired it this way. So moving forward, when we run this task, we're going to start our task, we're going to read the channel, and we're going to get the waveform out. And then we're going to process each one and get its name. Now, you wouldn't want to do this all the time because your name of your channel isn't going to change. So this might be something that you do only once, or only if this changes. For example, the dimension of this changes, maybe you'd want to reload the names there. And then as you can see, we're just wiring the data out to this chart. And you're going to see something very interesting. So this is our waveform names out. And I'm going to put it right alongside our indicator, and you'll see why in a second. And as you can see, I've already ran this program before, but let's go ahead and just rename some of these just to emphasize that this is actually working. So this is going to be test. Let's type in some gibberish for this one. Random letters. Go ahead and save that. So now we have a couple of different entries that we've changed, and now we're going to go ahead and click run. And as you can see immediately, obviously we're getting our data, but more importantly, our chart automatically recognizes the names have changed. Additionally, we also are able to see that we're extracting the exact same value. So both this and this will do the same point. So in this case, the legend will automatically be able to extract that, and I have a strong suspicion that it only does that when the data changes. But in this case, obviously everything else that's greater is just going to be a generic plot with a number. So in this case, that's the easiest way to extract the name, and you might be wondering why that's useful. Because if you log it to disk, you're obviously going to have the channel names appended at the top, and obviously if you throw it to a graph, that's going to be already there, obviously, as it's updating. But if, for example, you want to do something like the following, so this is one moment where you might actually have value in this. So we're going to go ahead and just do some FFT analysis. So this might be something that you do in your own logic. So we're going to go ahead and do, it's in this palette. Where's the FFT? No, it's in analog measurements, sorry. And it's going to be mag and phase. So we're going to go ahead and do a very, very, very simple. So all of it's going to be default. We actually don't care about what the data is. In your applications, you might for sure for those applications care what kind of window it is, what kind of analysis it is. But in this case, we're just going to go ahead and show a very quick demonstration. We're going to have to obviously resize because there's going to be a lot of logic added. And let's go ahead and take our time signals, which we can obviously get from here, which is just a duplicate, like I mentioned, of the signals coming in over here. And we're going to use everything the same. So these are all default values. You can go ahead and explore this VI in detail, but this is just going to give you a FFT analysis on basically the frequency response of your time signals. In this case, it's just going to be a dummy sinusoidal wave. So you should see some very generic data. But in this case, if we go ahead and do this and just get the magnitudes, we don't care about the phase for now. Let's just get the magnitude. And let's actually not do it this way. Let's just do another chart. You'll see why in a second. Because if we just do it the way that I had it previously, you're just going to see numbers. In this case, we want to see a graph. And actually, sorry, it's going to be a graph, not a chart. So we're going to go ahead and do silver, graph, and then a graph. We're going to put it right here. And so this is going to make sense in a second. So if we wire this now, it changes because it's accommodating different input to this graph. And so let's go ahead and plot this. You'll see something very interesting. So if I just simply click run on this, you can see we're getting a frequency response on this. Obviously, I haven't changed the axis and the Y and X axis in terms of their names. Obviously, this isn't time anymore. This is frequency response. But we're going to go ahead and see that obviously you don't carry over these names, right? So plot 4 obviously is the same because there's no data there, but the first 4 don't have that. So for your indicator, you might actually want to display these values. So you're asking, well, why is it not just copied over? Because here the output has nothing to do with this anymore. You basically lose all of your attributes. So in the case that you want to actually label these correctly, you might want to go ahead and do something like the following. So let's stop this application and let's right click on our graph, and we'll do create property node, and we're going to go ahead and do active plot. So you'll see why this is going to be created in a second. So if we wire this, let's just make sure it's all wired in. And it's obviously important to always wire your errors. So we're going to do active plot, and then we're also going to do plot name. So the reason we need these two is because when we're changing the plot name, we need to know which name we're changing. And in this case, because we're doing it for every name in here. So we're going to do because obviously the size of this is going to be the same size of this because we're feeding in, let's say, four waveforms, and we're feeding out 4. They're not waveforms anymore, but 4 signals here for your FFT. So we're going to let the size of this array dictate how many cycles it's going to be, and then obviously we can just use our iterator here at the bottom to say active plot. So let's go ahead and do that. And so basically, by doing so, we're going to process every single plot and rechange its name. And obviously, we only want to do this in this case. Let's just do it on first call. So on the first time this logic is executed. The reason we want to do that obviously is because anything on the UI, so rechanging things, changing UI properties, anything property node, invoke node for UI elements is taxing on CPU. So we're going to limit that to only on the first operation, and we can't change those names, or we can, but we shouldn't change those names during runtime anyways. So we're going to go ahead and ignore that. And so when we click run, you'll see this happen where now instead of saying plot, you actually have the right plot. And this is just a quick, 5-minute version of how you can, 5-10-minute version of how you can implement naming on your UI on things that are not necessarily going to automatically name themselves. So just to recap, obviously, if you feed a waveform into a chart or a graph, it's going to automatically recognize that you have those names. And we can extract them, and so that part's redundant. But if you run it through FFT analysis, which is very common for engineers, or if you just do some post-processing where you're losing the waveform format and you're plotting the graph and you don't necessarily have that attribute anymore. I mean, this was the simplest example because it lost that attribute for you. But if, for example, you were to unbundle these, do some sort of operations on them, run it through some more complicated logic, post-processing, you would want to be able to load onto a graph or a chart and still maintain that name for that ability. Now, in a future video, we're going to show you also how you can take scaling and also attach it to this name. So we've had other requests and other comments about displaying scalings and displaying other values. When you're setting these names, I mean, this isn't limited just for plot name. You could do it for the plot name of a chart, for a graph, for anything where you have this legend. You can actually override this. So you don't have to have it be labeled what it's being labeled right here. If you really wanted to, you could, the same way that we're setting a plot name here, you could override that with plot name, and then in parentheses you can say times 3 plus 5. So in that case your scaling would be multiplied by 3 and then add that constant, right? You could do your linear scaling, or you could basically describe what scaling it is that you're doing. And again, this might not be useful in your application, but in some applications it might be. And it's very important to remember that those tools are available to us, and we can actually help our UI be a little cleaner, display obviously a lot more information, and not have to have notes and annotations, or potentially confusing plot 4, plot 5, where we don't know what that plot actually is. So this is just a quick way to go from your waveform to actually renaming, for example, an FFT to display that. So if you have any other questions, please leave comments in the comment section below. I'll be happy to answer them for you. I will be making more videos about variant attributes, or in this case waveform attributes, data you can extract about channels, about their scalings, about their offsets, about synchronization, anything to do with DAQ. It's a huge topic. There's dozens and dozens of videos I can make about various topics, but to help you guys and serve you guys better, please leave comments so I can know where to guide my efforts. And as always, please subscribe, show support, like the video, comment on the video, reach out if you have any questions, and I'll be happy to answer them all. Thank you very much.